This is video number 3 for sections 7.3 and 11.2, Introduction to Complex Numbers. To begin, let's take a look at this quadratic equation. It's similar to the ones that we've been doing. I can see that there's only one x showing in it, which means the square root method is a perfect candidate. Step 1 of the square root method is isolate the base and the power. Well, that's done. Here it is. The base is x plus 4. The power is a 2. That's all set. Step 2 is the biggie, right? Take the square root of both sides, so I can go right to that. Square root, square root. Don't forget the plus or minus. And then when I simplify, on the left side, square rooting a perfect square, I'll just be left with the x plus 4. And on the right side, I have plus or minus the square root of negative 45. Now, as soon as I write that down, you might look at that and think, wait a minute, the square root of negative 45, that's impossible. There's no way I can do that. I can't find a number that you can multiply by itself to get negative 45. This equation has no solution. And you would be mostly right. What do I mean by that? Well, technically what we'd be saying here is there is no real solution. By real, we simply mean you could not find a number on the real number line, the number line that we make often, that makes this equation true. There is no such thing on the real number line as the square root of negative 45. Well, a few hundred years ago, somebody said, what if we made up a new kind of number where the square root of a negative was possible? And so that's exactly what they did. Let me move down the page here a little bit. I'll come back to our equation a little bit later. But several hundred years ago, somebody said, let's create another kind of number, a different kind of number. And they called that number I. I is a number, and the definition of I is the square root of negative 1. Now, I can't find a spot on here to plot I. I is a different kind of number. It is often called the imaginary unit, which is an unfortunate word. We don't want you to feel like you're doing make-believe math. That's not the case at all. The word imaginary is simply used to contrast with the word real. It's a different kind of number. Well, if the square root of negative 1 can be called I, then when I see the square root of negative k, that negative 1 in there becomes the I, and I'd just be left with the resulting square root. Square root of negative k can now be written I times the square root of k. Maybe better, square root of k times I. We just like to put the square roots at the end so there's no confusion about what's inside. Let's use this definition, these new definitions, to work out some examples. Prior to the world of complex numbers, you would have had to look at these three examples and say these things are all impossible. And that's true in the world of real numbers, but I can actually work these out in the world of complex numbers. For example, the square root of negative 5. Well, that's an exact match for this second definition. According to our definition, this is simply equal to I root 5. That would be the simplified version of square root of negative 5. How about square root of negative 9? Well, that would be I root 9. Of course, this one I can keep going because the square root of 9 has a nice answer. The square root of 9 is 3, and I times 3 would be 3i. Again, I always put my coefficients at the front when I can. The third example, square root of negative 12, well, I can do I square root of 12. And then I notice square root of 12, 12 has a perfect square that goes into it, namely 4, which means I can break this down further as square root of 4 times square root of 3. Square root of 4 has a nice answer. It's 2. So on the outside, I have I times 2, which is 2i. And then I have 3 on the inside of the radical for a final simplified answer of 2i times the square root of 3. So this new definition gives me a way to take square roots of negative numbers and continue on with them. Well, let's go back up to the equation. Now that I have these complex numbers, I can continue to solve this equation. I have a little bit of algebra that I need to do. I need to subtract 4 from both sides. And that gives me x equals negative 4 plus or minus the square root of negative 45. And then I can simplify this square root using what we just learned. I would get that I that would come out because of the negative sign on the inside. And then the square root of 45 would be left inside. But the square root of 45 can be broken down further. 45 has a perfect square that goes into it. And so I can break that into the square root of 9 and the square root of 5, right? 9 times 5 is 45. The square root of 9 is 3. And so what I end up with in the end, I times 3 would be 3i, and then times the square root of 5. Here are the two final solutions to the original equation in the world of complex numbers. There's certainly no reason to find decimal approximations in this case. These are not real numbers, they are complex numbers. Let's conclude with just a little bit of a definition of what exactly a complex number is. A complex number is a number that can be written in the form a plus bi. A and b are just regular real numbers. I is this square root of negative 1. Well, if you look carefully at the two numbers we just ended up with, they both fit this pattern. In the first number, the a is negative 4 and the b is 3 root 5. Right? It says negative 4 plus 3 root 5i. Again, we put the root at the back so that there's no confusion. That would be my a and my b. In the second example, the a would be, once again, negative 4, and the b would be negative 3 square root of 5. It's negative 4 minus 3 root 5i. Anytime you have a number in this format, we call it a complex number. This stuff may seem strange to you, and admittedly it is a little strange. Amazingly, though, in the hundreds of years since this stuff began, there have been numerous applications involving complex numbers, including in real-life situations in higher math and science. Now, when you're doing the homework, this is very important, and they ask you to solve a quadratic equation, you just need to pay close attention to the directions. If the directions say, find all real solutions only, then you would have stopped early on in this problem and said there aren't any. There is no real solution, end of story. But if the directions say find all solutions real or complex, then they want you to take it all the way down to the end, even if that means the solution involves I.